So, when we say synthesis of alkene, we mean how do we make alkenes? And we've done this before. In the previous chapter, when we were talking about SN2, SN1, E1, E2 reaction, elimination reaction in this case is talking about alkenes. Making alkenes is simply doing elimination reaction, whether it's elimination in the first order or whether it's elimination in the second order. So most of the time when we're doing a reaction here, we're kind of referring to the E1 and E2 elimination or E2 reaction. So the first one I want to introduce is called dehydrohalogenation. Dehydrohalogenation, just like it sounds, I am removing, right, a hydrohalide. X represents any of the above, right? X represents, if I'm talking about chlorine, bromine, iodine, or fluorine. So any one of the halides. Right? That's what X is talking about. Let's put X as a red, so you know, right? Hydrogen, you know, right? This the simplest atom, so it can also form P. Lewis acid, so it can easily be H+. Since all the halides are good living groups, we'll see how the reaction occurs here. So let's see. A typical double bond is made. Let's see this reaction. What do we have here? Right. We have a secondary alkyl halide here. Right. And all we're doing here is adding heat. Right. As soon as we add a heat and some base, doesn't matter what type of base, right? Any heat with any type of base, any strong base. Let's use what if we use T-butoxide? It's a good base, very strong. Breakable far, but a very good base. If you want to make this into a base, immediately just break it apart. Always break it apart to this counter ions. Once you break it apart, you see that this is a very strong base. Under basic conditions and this heat, you're going to have this leave and automatically making the E2 elimination, because this is going to be your alpha hydrogen. Right? This is your alpha hydrogen. This is leaving. All this is doing is coming here as this is leaving, and then you have your double bond. Right? Don't forget that this is another. Keep forgetting that this is an organic molecule, so even though you're making your double bond, you're also making a tertiary alcohol. Please don't forget that as your product. But what we're concerned about, we're making this alkene there, right, from this reaction. What kind of reaction is this? If you remember, this is an E2 elimination, right? This is the E2 reaction here, right? E2. If you remembered, right, from previous chapter. It's E2 because what am I using? I'm using a strong base, right, to eliminate the alpha hydrogen. I'm using a strong base in a secondary alkyl halide, whether it's secondary or tertiary, E2 will work for it. All right. Well, let's see another reaction. What if we do dehalogenation? Right. Dehalogenation. Dehalogenation, just like it sounds, right, is, let's pretend we have, let's see, this being the case here, an anti-addition, bromine here, and some R group and an R prime, we don't really care. We got H here, we got H there, right? Okay. So we have two bromines, right? And we want to eliminate that to form or to synthesize an alkene. What do? Well, you can either use sodium iodide under some solvent. In this case, I'm going to use acetone. Acetone sometimes it can be written just as acetone. This is what acetone looks like. Acetone is a carbonyl group. Right. This over here is a carbon. Remember that? Right. Acetone. Now, when you're using this, you're using the solvent, but what happens actually? Let's kind of like look at the mechanism. Right. Again, break this apart. Sodium. This is iodine. Iodine ion. Here you have this attacking one of the bromine. So let's say it's attacking this one, right? This one is going here, and that one is leaving. It's a quick reaction because now what do you have as a counter, as your ions that you just formed? Minus IBr, right? So that's forming. You have also formed sodium bromide because that's sodium is plus, bromine that is coming out is minus, and of course your organic product, which is now into an R prime. This is an R group with a double bond. Right? If you ask me, this is trans, right? This is a trans molecule if you're assigning isomers to it. Right? They're both pointing in the opposite direction. Alright, that's called dehalogenation. If I'm using bromine here, this is debromination. If it's chlorines are here, dechlorination. Whatever is here. Right, so we're talking about halogenation. Right? Dehalogenation. Alright, the next one I'm going to do is called dehydration. Dehydration is exactly what it sounds like. Right? If you're thirsty, what do? You drink water. So if you're losing water, then you're dehydrating. So same thing here. So anytime you have an alcohol, right, to lose the alcohol, we're going to do a process called dehydration. Simply, you add this acid called H2SO4 under certain degrees. You don't have to remember 150 degrees, but just under heat, right? Always remember that this is always broken apart. Never leave this. This is H plus. This is cation. Right. What's gonna happen? The H plus here, right? The oxygen is going to attack the H plus. Once attacked, right? It's gonna go form water here. This is the plus. Right. Now what happens? So what you have here is you have a plus here, right? That does not want to stay there. So what happens? This is going to leave. Right. By leaving, you create a cation. You created a cation. Remember, you have an alpha hydrogen there and an alpha hydrogen there. I don't want to make that one because I want to make a very stable one. So what happens? The base comes and takes that. You can either use this base or you use water. It's up to you. And then you take the hydrogen and you form this as your product. This is your, what kind of reaction is this? This is an E1 product, if you were to name it. Right? Because what are you using to make this? You're using water, which is a very weak base and a very weak nucleophile. So most of the reactions that's going to happen in this chapter is pretty much going to be either E1 or E2 elimination. So the rules that apply to E1 and the rules that apply to E2 also applies here when you're making your product. Okay. All right. There's another reaction I want to introduce called Hoffmann. Right? It's called Hoffmann or Cope reaction. Hoffmann. By this guy named Hoffmann. All right. Hoffmann is using silver oxide as a reagent. Right. So let's say we have this molecule as our reactant, and we are attaching it with the Hoffmann reagent. By doing that, obviously we still need what? Heat. Most of the time when you're trying to form an alkene, because you're breaking bonds to form alkenes, you're going to use heat. There's some rearrangement going on, right? So for this reaction, all this does is to remove whatever this is over here, nitrogen containing atom or compound there. It removes that, and then you form alkene with the carbon. And all you have left is whatever is left over there. And that's simply it with this reagent. For this reaction, I just want you to know, whenever you're having this reagent react, whatever is attached to that carbon, you form an alkene, wherever it is. So here, between those two carbons, wherever it's attached, right? You form an alkene there. Not too much science to that, right? And then lastly, I want to introduce how to go from alkyne to alkenes. Well, we are talking about alkenes, but for the sake of this, since we're still making alkenes, I'm going to introduce alkyne. Alkyne are triple bonds. From what I've told you about triple bonds before, triple bonds, what are triple bonds? They are linear, and they're 180 degrees, right, in bond angle. So, and they're shorter in bond length. So if we were to measure the bond lengths between single bonds, double bonds, and triple bonds would be the shortest bond length, right? And the hardest to break. So when we're doing this reaction, we're going to introduce how to convert this into what? Double bonds. Let's see. If I were to convert this to double bonds, I'm going to use hydrogenation method, which is using H2. That's a diatomic element. I'm going to use barium sulfate, and I'm going to use some catalyst, either platinum, either palladium, or one of the both. Right? Using these specific reagents, I'm going to allow these hydrogens to be able to attack. Let's pretend that let's ignore all these other reagents and just look at what hydrogen is doing. These reagents allow hydrogen to both act as an acid and as a base. So let's pretend for a second, right, that there's a type of pull or hydrophobic reaction going on between hydrogen and hydrogen. Electron density is trying to pull between them. Let's say that this one wins and we get a negative sign here, and that is a positive sign. Let's say that, right, based on whatever is going on over here. And let's say that because this is a base, this is going to attack the acid. Because this is an acid, it's going to attack wherever you have a positive sign. Because if you're attacking the acid over here, there'll be a positive sign that's going to be forming on the bottom. So by doing that, you just created a double bond. As simple as that. Right. But the main fact that we're using the whole reagent here is because of this. So I'm going to show you why we're using this. Let's pretend that instead of this, I have an R prime, and over here I have an R. Okay, let's show that. What happens is that this would have formed an R prime and an R. Because if you notice, this will form this into a cis. That's the main reason why we're using this reagent. The way the reactivity of this happens causes this to form into a cis product. So whenever you use this reagent to convert an alkyne, alkyne is spelled this way, which means triple bond, you're forming a cis alkene. All right. We won't go into details of this now. We'll go into these reactions when we go into the chapter of alkynes. But I just wanted to introduce it in alkenes, so you see how we synthesize alkenes from alkynes. All right, that concludes the nature of synthesis of alkenes.